floor 5, the final floor, right? So what you have in floor 5 is, so in the feed-forward neural network, we had a 512-dimensional vector go through the first fully connected layer with activation function you get. In the paper, they say they have a 2048 dimensional, so it increases the dimensionality, and then the second fully connected layer reduces the dimensionality back to 512. So as an output of the fourth floor or fourth level, and as the input of the fifth level, we have we're back to a 512 dimensional vector for each word. There's 6 of them in our sentence. Now, what we want is we want to map that to predict the next word. So we need that to map that to the vocabulary, to our vocabulary, which, like in the English language, let's say 200,000 words. So in the fifth level, in the fifth and final level, we have a linear transformation plus a softmax function. The linear transformation is designed to map the output that we have so far, the 512 dimensional vector, to 200,000 words, to 200,000 nodes. So it takes basically, it's a neural network layer that has 512 in the input, no activation function, and it maps it to a 512 fully connected layer, maps it to a 200,000 layer with 200,000 nodes. Right, so we get those outputs. They're called logits. They're unnormalized, just outputs in these in this neural network layer. And then after that, we pass them through a softmax function, very similar as we discussed in the attention mechanism softmax function. And this is our second softmax function for the transformer. Basically, what it does is it takes all those logits, those unnormalized values. We got 200,000 of them, one for each word in the English language, and it each one goes takes an exponent of each one and then divides by the sum of those exponents. So basically it creates a probability distribution. Now we have 200,000 values in a probability distribution, which in total add up to 1. And those values are representative of what is the probability for each word of the English language to be the next word in this sentence. But remember, this is a key. This is very important part of transformers. Something took me a while to figure out or wrap my head around. Like I had a big breakthrough myself, literally yesterday on this. We had 6 vectors going into this fifth and final level, and then we applied the linear transformation. It was applied to each vector independently, and we applied the softmax. It was applied to each of those, vectors or whatever we got, those 200,000. For each vector, we got 200,000 of values after the linear transformation. And so the softmax was applied, we applied it 6 times. So we have 6 probability distribution. 1 for the word apples, 1 for the word R, or 1 as a result of the vector that we had for the word apples. We have a probability distribution of 200,000 values. Then we have another one as a result of the vector we had for the word R, another probability distribution of 200,000 values. And another one, and all the way up to delicious. We have for delicious, we also have we had a vector, which was then converted into a probability distribution with 200,000 values, which add up to 1. So that's a very key, important thing. Now, in order to predict the next word in the sentence, we're going to take the probability distribution of the last word, of the word delicious, and we're going to use those probabilities, and we'll just take the word with the highest probability, and that will be our next word. So in this case, it will be fruit, right? So that we want the transformer to know that that's once the transformer is trained, the word fruit will have the highest probability in the probability distribution that came from the context-rich vector of the word delicious. The other 5 probability distributions, we're just going to throw them away. We don't need them. They're not used in inference. They're absolutely useless during inference.
So but they are useful for training.
They are.
Like, is that what we can?
Yes.
Okay. Because I was like, why are we doing all that compute for nothing? Someone should have thought of this.
I know, right? I know. Like, so imagine if you have an input of 100, like 1,000 words, like a context. That's why context window, is hard, because like if you have 1,000 words input, you're going to have 1,000 probability distribution. You're only going to need the last one of them, right?
For inference.
For inference, exactly.